Chapter 7 was estimation, theory of estimation. Chapter 8, which we start today, gets into the heart of inferential statistics. And our two big topics in inferential statistics are confidence intervals and hypothesis testing. You did one problem with the confidence interval for today's assignment. You'll have more for Thursday's assignment, as well as next week. This is the big week in terms of getting the foundations of statistics right, inferential statistics. But let's start by working through some of the problems that you had for today and relating it to both the theory and maybe more simulation. We want to continue talking about the importance of understanding the theory and understanding simulation. So the first problem let's do is number 46 that you had for the assignment today. Let X denote the time required to do a computation using an algorithm written in programming language A, and Y is the time required to do the same calculation written in programming language B. We're wondering, how do these programming languages compare? We assume, maybe based on past behavior, past data, that X is normally distributed with a mean of 10 seconds and a standard deviation of 3 seconds, and Y is normally distributed with a mean of 9 seconds and a standard deviation of 4 seconds. You know, these days, if anything takes longer than a tenth of a second, we're like, why is this calculation taking so long? But in the olden days, that might be more typical to take a certain number of seconds. And maybe if the algorithm is complicated enough, it still could take a little while even today. Part A, what is the distribution of the random variable X minus Y? And part B, find the probability that the given calculation will run faster using A than when using B. This is kind of related to the example Dr. Wetzel shared when he compared his bowling scores with his wife's bowling scores. You've got two different normal distributions with different means and different variances. So X is normally distributed with a mean of 10 seconds. Standard deviation of 3, so we would write the variance as 3 squared, which of course you could write as 9. And Y is normally distributed with a mean of 9 seconds. It's a little faster. That's programming language B on average. Standard deviation, however, is a little bit bigger, 4 instead of 3. Variance is 4 squared. So for X, the normal curve that is modeling how long it takes for this algorithm to run is centered on 10 and has a standard deviation of 3. Thinking in terms of the inflection points on the graph, right about there and right about there, that would mean this value would be 13 and this value would be 7. That's one standard deviation away from the mean right there. And Y is normally distributed with a mean of 9 and a slightly bigger standard deviation of 4. 9 minus 4 is going to be 5, putting you right about here, say. 9 plus 4 is going to be 13. The Y is a little bit more spread out, so its graph to have a total area of 1 would have to be a little lower. It's a little bit more spread out. I'm being a little extreme here in my drawing. Inflection points of Y are in those spots. So it should seem reasonable that, yeah, on average, let's see, smaller number is faster, right? This is the number of seconds to run. Y is a little faster on average, 9 seconds compared to 10 seconds. But there are certainly going to be plenty of times where X runs faster than Y. You can tell it intuitively just by these graphs. What is the distribution of X minus Y? Call it W. Do you have intuition about what the answer should be without looking in the book? It is going to be normally distributed. I've given part of it away here. Without looking in the book, do you have intuition about what the mean would be? Just take a guess. It should be a relatively easy guess. 1, yeah, 10 minus 9. Just subtract the means. Do you subtract the variances too? No, you don't. What do you do? By the way, I am assuming X and Y are independent here. I forgot to mention that very important assumption. That's always the assumption we make in this class. You can do prob and stats without that assumption, but it's a lot harder. So we're hoping most situations it's reasonable to assume your random variables are independent. These programming languages are running independently of each other. I guess that seems somewhat reasonable. What do you do with the variances? You remember? You don't subtract them. Go ahead. You add them. 3 squared plus 4 squared. So this is normal with a mean of 1 and a variance of 9 plus 16 is 25. Hey, that works out nice. 5 squared. Why? Well, according to the theory that we've been doing in the homework you had for today, there's a homework problem. In the most general form, it's number 41 here. That if you got a random sample of normally distributed random variables, well, actually, it's not a random sample because they don't all have the same mean and the same variance. Mean mu I, variance sigma sub I squared, and you form essentially a linear combination of them with a constant in front as well. It's like a linear combination of vectors from linear algebra. That you've essentially, to get the mean, you do the same linear combination of the individual means. And well, except for the A0 being missing, a linear combination of the variances, but you got to square the coefficients. In our problem here, W is X minus Y, the coefficients are 1 and -1. A1 is 1, A2 is -1. Same kind of linear combination of the means, 1 times 10 plus -1 times 9, 10 minus 9. And then 1 squared, you don't see a 1 squared, but it's there implicitly, times 3 squared plus 1 squared times, or -1 squared times 4 squared. The coefficients, the A's, are 1 and -1. You add them. It certainly couldn't be subtracting. It would have to. It couldn't be subtracting because if you subtracted them, you get a negative variance, and that's not possible. It does turn out you add them. You don't add the standard deviations, though, right? Standard deviation is not 3 plus 4. It's not 7. It's 5. Right? You know, of course, square root of 3 squared plus 4 squared does not equal 3 plus 4, right? Common mistake you'll see from statistical analysis students, the business stats students, is they, for some reason, think that. Got it in their head that they think they need to do that. But no, that doesn't work. You can tell by the numbers involved. You add the variances, but you don't add the standard deviations. But you can still figure out the standard deviation. Anyway, part B is to find the probability that the calculation for A runs faster than B. A corresponded to X and B corresponded to Y. So A running faster is a non-typical situation. X being less than Y means A runs faster than B. Well, rewrite it in terms of W. This is the same as the probability that X minus Y is less than 0, which is the probability that W is less than 0. W is normal with this mean and this variance. Standardize if you want to do it by hand. Subtract the mean, divide by the standard deviation. You're going to get a little less than 0.5, as you would expect. Because on average, Y is smaller than X. B runs faster than A. Looks like we get that. Let's just use the calculator here now. About 0.4207. That's probably too many significant digits. Probably want to round out to 0.42. Yeah, on average, y is smaller than x. X is bigger than y on average. But there is a fairly high probability, not bigger than 0.5, but still fairly high, reasonably high chance that x could be smaller than y on a certain situation, in a certain run of the experiment. Is there another way we can try to believe this? Sure, with simulation. Let's try simulation in a spreadsheet. So we're going to look at observed values of x and observed values of y. Maybe we'll do 100 samples of size 100 or something and count how many times x is bigger than y. Why is this good to do? Well, for one thing, it can reinforce that you really understand what's going on. For a second thing, especially if you're in the job and you're worried you might get fired if you do something wrong, that probably won't happen, but I mean, you know, people make mistakes. But maybe your job's on the line or something and you want to try to check, is my theory okay? Does simulation confirm my theory? Does it seem about right? That's one thing simulation could be good for. Another thing that's good for is sometimes theory is just too hard, but simulation maybe is not so hard. In fact, I've got a video on this. You can look it up. I made a simulation of chutes and ladders. Like how many spins does it take you to win a chutes and ladders on average, based on where the chutes are, which are the slides going down, and ladders going up. You've played chutes and ladders, right? Okay. Kids game. You can play it when you're 3 or 4 years old. It's not something you could theoretically assess very easily. How long on average does it take you to finish? But you can simulate it with a program. Anyway, coming back to this problem. So x again was normal with a mean of 10 and a variance of 9, and y is normal with a mean of 9 and a variance of 16. How can we do simulation? What do we know so far in a spreadsheet? We know equals RAND, don't we? And we did 10 times RAND last week to do a uniform distribution on the interval from 0 to 1. How in the world could we simulate a normal distribution? Well, it's with a creative use of RAND and NORMINV, which NORMINV is essentially the same as the thing on your calculator that is inv norm. A calculator, inv norm, gives you a z value, at least if you use a mean of 0 and a standard deviation of 1. When you know the CDF value, say 0.9, that's the area to the left of a z value on the axis where the area under the curve is 0.9. What kind of z value are we going to get here? Something bigger than 1. I forget exactly what. It's one of those famous numbers, either 1.28 or 1.645 or 1.96. I think it's the 1.645. Oh, 1.28. Okay. That number, z equals 1.28, is a number on the horizontal axis for a standard normal curve where the area under the curve to the left is 0.9. The CDF value, if you plug 1.28 into the CDF of a standard normal, you get 0.9. NORMINV on a spreadsheet does the same thing. If I plug in a 0.9, mean of 0, standard deviation of 1, there we go, 1.28. If instead of 0.9, I plug in RAND, that's giving me a uniform number, a random number between 0 and 1 to represent the area to the left of a given z value. So this is essentially giving me a random z value now in the end with a mean of 0. Oh, well, let's use the mean and standard deviation given in this problem here, 10 and 3. This is now giving me a simulated value of x. And as usual, if you copy and paste, it changes. X's mean is 10 and variance standard deviation is 3. Can do something similar for y. NORMINV. Now use, okay, if we still use RAND here, now use a mean of 9 and a standard deviation of 4. So typically y is going to be smaller than x, but sometimes x will be smaller than y. Okay, copy and paste this down, get samples of size 100, say. And then, okay, so yeah, typically y is smaller than x. It is here, 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 here. On average, y is smaller than x. We could also look at the value of x minus y. And what should we expect to see in samples of size 100? Since we found a probability close to 0.42 for x being smaller than y, we should expect maybe about 42 out of 100 will be negative. Will it be exactly 42? I'm sure it will not be exactly 42. And again, it always changes as you copy and paste. Is there a way to not have to actually go through this list and count how many negative signs you see? Yeah, you can do something equals count if. Syntax here, I think, is in quotes, put a less than a 0. In this particular run, you can see there's a 45, but if I enter it, it's probably going to change. 37, do a copy and paste again, change it again, 47, copy and paste again, 29, 39, 34. Sometimes it's bigger than 42, sometimes it's less than 42. But doing this enough is helping me believe that 42 might be a decent answer. 42%. Okay. Do a bigger sample sizes if you want more confirmation. Maybe samples of size 10,000 or something. Combination of theory and simulation. Let's continue combining theory and simulation. Let's look at 45, which is going to be important for today's class. Going backwards here, it can be shown that the square of a standard normal random variable has a chi-squared distribution with, what's that? 1 degree of freedom. Little gamma is 1. In the problem, you're ultimately based on that trying to show this has a chi-squared distribution with n degrees of freedom. Actually, let's dwell on the first part, this claim. They say it can be shown, so you were supposed to just trust that. If you square a standard normal random variable, you get a chi-squared random variable. Actually, I haven't tested this with a spreadsheet before, but let's see if it's possible. Let's generate some z values. Z is normal, mean 1, variance 1. I could do the same kind of thing with the NORMINV, RAND, but now do 0, 1. Can I do I can certainly square that. Oops. So I'm squaring the output of a standard normal, an observed value of a standard normal there. Is there a chi-squared inv or something? I don't remember. There is a chi-inv. Maybe that'll do it. I can type. I bet that will do it. So let's get 100 values of z. Copy and paste. So we're just trying to believe it and also trying to understand it. Do we really understand it right when I'm doing it this way? So those are 100 different simulated values of the standard normal random variable. In this column, I'm squaring them to, according to the book, get 100 simulated values of a chi-squared random variable with 1 degree of freedom. How would I test that? We don't really have the tools to test that rigorously, but let's just see if we compare it with simulating CHIINV like this, if we get comparable sets of numbers, maybe with approximately the same mean and approximately the same standard deviation. So this equals CHIINV with RAND should, and comma 1, should simulate a chi-squared random variable with 1 degree of freedom, I think. So in columns F and G, we essentially should have 2 samples of 100 that are roughly the same in their behavior. If I made histograms for them, they should be roughly similar in shape and center and spread. But instead of making histograms, let's just compute the average, F2 through F101, and the standard deviation for both columns. What happened there? Did I type that wrong? Oh, here my 101 didn't. Is that it? Okay. If I copy and paste this to the right, it'll go do it for column G as well. So what I'm hoping is that these numbers are relatively similar. Yeah, not too far apart. Copy and paste again, do another simulation, do it again. I mean, it's not perfect, but it's reasonable enough to help me believe it. You get what I'm doing here? I'm trying to confirm the theory, make sure I understand the theory. And if I didn't know the theory, or maybe I had to guess about what the answer might be, this could help confirm that the guess seems about right. Let's do some theory now, though, too. Claim if Z is standard normal, that implies its square is chi-square with 1 degree of freedom. Let's call this W. You remember last week? Maybe it was a week ago. I used something called the CDF method. I confirmed a distribution by finding the CDF and then differentiating it to find the PDF. I forgot what the context was. I forgot what the example was. I'm going to do that again here. It was an example where I think we were adding 2 uniform random variables. That's what it was. On the interval from 0 to 10 about a week ago. Adding them up, and so we saw that we got a triangular distribution. I used the moment generating function approach to confirm that. And we also used the CDF method to confirm it. We got piecewise functions. We had to differentiate the piecewise function. Seems like 3 weeks ago, but I think it was a week ago. Let's do the same kind of thing here. CDF method to find the CDF for W. And then differentiate it to find the PDF. And what are we hoping? We're hoping it's a PDF for a chi-squared random variable with 1 degree of freedom. That's what we're hoping. And I said, when you use this method, you always want to use the fact that the CDF is always the probability that your random variable is less than or equal to the given number, in this case, little w. And then you just got to work from there. If it's a continuous random variable, that could mean doing an integral here. If it's a discrete random variable, it could mean doing a summation. This is continuous, Z is continuous, so W is continuous. So I guess we got to do an integral. Well, maybe we can avoid doing an integral. I mean, the only thing that seems logical to do at first is just replace W with Z squared. Because we're trying to relate it to Z. I mean, we're assuming Z is standard normal. So we know how to compute probabilities for Z. theoretically at least. But it's a z squared. How do you get rid of that square? Take the square root. Yeah, but you got to be really careful because z could be positive or negative. So I don't say this is the same as the probability that z is less than or equal to the square root of w. I don't say that because z could be positive or negative. What it's equivalent to is that z would be between negative square root of w and positive square root of w, since z could be positive or negative. And I can also use the fact that the normal distribution is symmetric about 0. It's an even function, the PDF. So I could do 2 times the probability that z is 2 times the probability that z is less than or equal to square root of w and also greater than or equal to 0. I could do this. That might make it a little simpler, maybe. I could ultimately write that as 2 times, in parentheses, the probability that z is less than or equal to square root of w minus the probability that z is less than or equal to 0. Standard normal, this would be 0.5. And well, if I want to use that standard normal CDF notation, this is not required. I could use it. I could use a capital phi of square root of w. That's special notation for the CDF of a standard normal random variable. It's not telling you anything that's not standard here. Pun intended. That is the CDF for standard normal random variable. That's the symbol for it. People use it. So where am I going with this? Okay, so I guess I get 2 times capital phi of, instead of writing square root of w, let me write w to the 1/2 because we're going to differentiate this thing. Distribute the 2 through 2 times 1/2 is 1. Isn't this fun? The CDF of w is 2 times the standard normal CDF evaluated at square root of w minus 1. Do I need the formula for that CDF? No, you don't. Actually, is there a formula for it? Yeah, kind of, though it involves an integral. It's not a elementary function. It involves ERF, right? I showed you ERF before, right? Error function. It involves ERF. But I don't need a formula for it because I know its derivative. Let's differentiate now. Little f sub capital W of little w is the derivative of capital F sub W of little w, which by the chain rule, and this fact that it equals this is going to be 2 times the derivative of capital phi applied to square root of w times, yeah, by the chain rule, 1/2 w to the negative 1/2. The 2's cancel. I could write this as capital phi prime of the square root of w divided by the square root of w. Interesting. How is it useful? Maybe I should. Yeah, this is the CDF for a standard normal random variable. There's its derivative. Maybe I need to look up the PDF for a standard normal. I'm getting excited here. I think I can feel we're getting close. Look up the PDF for a standard normal. This is supposed to be fun too, by the way. I'm having fun. This is like the thrill of discovery in math. What's the answer? What's the answer? Is it right? Right? You've experienced that sometimes. Is it right? Is it right? Standard normal. PDF for a general normal with mean, mu, and standard deviation sigma is that. Mu is 0, sigma is 1. Plug in mu equals 0 and sigma is 1 in there. What are we going to get? 1 over the square root of 2 pi. It's exp in the book for typesetting purposes, but I'll write e. It's negative x squared over 2 sigma squared, but sigma is 1. X squared over 2, but I need to replace x with square root of w here. And then don't forget to divide all this by square root of w. Simplify. I think I want to bring that square root of w into the top as a w to the negative 1/2. This is looking promising, I think. Chi squared and exponential are both subdistributions of a gamma. You remember gammas had formulas kind of like this? Or what are we hoping again? We're hoping this is chi squared with 1 degree of freedom. Chi squared. Little gamma is 1. A 1/2 minus 1, that's negative 1/2. Negative x over 2, that's like my negative w over 2. The only thing in question is this part. Capital gamma of 1/2. 2 to the 1/2. Is that what we got there? Oh, square root of 2 is 2 to the 1/2. That's 2 to the 1/2 here. That's 2 to the gamma over 2. What about the square root of pi? Is that gamma, capital gamma of 1/2? Question mark, question mark. Try it out with Mathematica. Mathematica knows everything. Gamma of 1/2, square root of pi. What? Square root of pi? How can that be? Where does the pi come from? It's a mystery. You should explore it. Explore why capital gamma of 1/2 is square root of pi. There's a weekend project for you. Not worth any extra credit, but just for your own joy. See if you can figure out why capital gamma of 1/2 is square root of pi. Yes, it's not question marks. Yes. This is the PDF for a chi-squared random variable with 1 degree of freedom. We're done. Did we use the fingerprint theorem? No, no moment generating functions, but we confirm the PDF is the right PDF. Keeping you awake at least? This is as fun as it gets in this course, I think. My opinion, or last week was supposed to be the most fun, but this is fun too. I mean, this kind of fits with last week. It's still chapter 7. Combined with chapter 4. Simulation and theory. I do still want to talk about the central limit theorem today, but we're going to save that for later. Instead, what I want to do right now is use that problem as a jumping point into chapter 8. So again, this is the problem we were just thinking about now. We just did the first sentence. That last 15 minutes is just this first sentence. You didn't have to do that for your assignment. It can be shown. We just showed. The square of a standard normal random variable has a chi-square distribution with 1 degree of freedom. By the way, we did not use the fingerprint theorem there. And if you think about it, it'd be hard to see how you'd use the fingerprint theorem because we used the fingerprint theorem in conjunction with the theorem about moment generating functions of sums of random variables. So we didn't use the fingerprint theorem, and it's hard to imagine actually using it there. Again, because it's not a sum of random variables. Z squared is not Z plus Z. It's Z times Z. So we needed some other method. The rest of the problem is related to the moment generating function stuff. X1 through Xn is a random sample from a normal distribution with mean, mu, and variance sigma squared. Use exercise 44 to show the sum is chi-squared with n degrees of freedom. 44 says if you add independent chi-squared random variables, you get a chi-squared random variable with degrees of freedom being the sum of those. Question? Yes, thanks. On my phone, you meant, right? Yeah. Yeah, it would freeze if it didn't. Thanks for telling me that. Zoom is recording overall, but my phone would freeze if I didn't do that. It is unfortunate the Zoom is a little herky-jerky with its recording, but we're okay. Anyway, where was I going with that? This leads into chapter 8, because the very first fundamental fact in chapter 8 is related to what we just looked at. By the way, plenty of typos in this book. I've got some typos circled. Very first theorem is this theorem. Some typos are above here. The motivation for the theorem is what they say here. Here's a typo. This should be an I, not a 1. Beginning of chapter 8, page 260. Chapter 7, number 45, that's the problem we just looked at. This summation is a chi-squared random variable with n degrees of freedom. The next theorem shows that if you replace mu with x bar, same kind of formula there, still a typo, that should be an I. You get a chi-squared random variable again, but now it's got n minus 1 degrees of freedom instead of n. That's mysterious. What did we do? We replaced mu with x bar. That's all we did. These are two different random variables here. These summations could be thought of as being random variables. In fact, they could be thought of as statistics because they come, if x1 through xn is a random sample, these would be statistics. To compute this one, you'd have to know mu and you'd have to know the variance of the population. To compute this one, all you need is the variance of the population, not the mean. I mean, you might still argue this is unrealistic to be able to compute this because how would you know the variance? But we're trying to build up toward more realistic things here by thinking about less realistic things. We lost a degree of freedom. Why? That's what this theorem say. Why? The proof is in Appendix C. Uh-oh. Proof is in an appendix. Must be hard. Should we peek at it anyway? Proof of theorem 8.1.1, Appendix C. Page 783, 784. There's the theorem. Here's the proof. Oh, just four lines? Oh, no. The proof goes onto the entire next page. Almost. Yeah. Yeah, we'll skip that. For class, at least. Another weekend project is to go through that and make sure you understand it. It's one of those things where, again, where you can maybe follow every step, but it's like, how would anybody ever think of this in the first place? And maybe it doesn't give you much intuition. But still worthwhile to see that somebody figured it out. So if you replace, again, the theme is if you replace mu with x bar, you'll lose a degree of freedom. Actually, this is something we've already seen a little bit of before. When you compare the variance estimator where you divide by n, and instead divide by n minus 1, that's essentially losing a degree of freedom. To get the unbiased estimator, s squared, n minus 1 could be called the degrees of freedom in that case as well. And we lost one. In the formula for s squared, back in chapter 6, they don't call it degrees of freedom there. Compare this formula with that formula. Dividing by, we never use this formula, by the way. Page 207, we always use this one. Page 205. Got to divide by n minus 1 to get an unbiased estimator for sigma squared. It's kind of like you're replacing mu with x bar there and losing a degree of freedom. Okay, that doesn't really explain much, but it's a kind of similar idea. We could try to believe this by simulation again. Where'd it go? We could try to believe this theorem by simulation. For the sake of time, I won't. Let's try to imagine doing it. X1 through Xn does need to be a random sample from a normal distribution. Mean, mu, variance, sigma squared. So if it's going to simulate it on a spreadsheet, I want to do the NORMINV and the RAND. Pick a mean, pick a variance, just for the sake of example. Get a bunch of observed values of these x's. Would I want to compute this side or this side? Probably it's easier to compute that side. They're equal to each other. I mean, in theory, you could do both. They would be equal. The reason these are equal is because of the formula for s squared back in chapter 6. The theorem is not that these are equal. The theorem is that this random variable has a chi-squared distribution with n minus 1 degrees of freedom. That's the theorem. These are obviously equal when you replace s squared with its formula. The n minus 1s cancel, for example. Yeah, that's the key. That's the key reason these are equal is the n minus 1s cancel. You could compute this based on your assumed mean and assumed variance. You just use the variance, in fact. And then you have to compare with CHIINV and n minus 1 degrees of freedom. You'd have to compare those two columns like I did 25 minutes ago, when there was 1 degree of freedom. And see, make histograms, see if they seem about the same, see if the mean and standard deviation of those are about the same. That would help you believe this. We just want to use it. The thing they use it for is to come up with a confidence interval to estimate a population variance. Let x1 through xn be a random sample of size n from a normal distribution. For this to technically be right, it's got to be a normal distribution. It's the population. However, that's what makes this a theorem, makes it provable. However, people do apply this to situations where they're not quite sure if it's normal or not. It just seems like a reasonable assumption to make. This always goes on when you're using statistics, right? Is that a reasonable assumption? If it seems somewhat reasonable, I'll go ahead and use the theorem. Then lower and upper bounds, left and right endpoints for a confidence interval to estimate sigma squared are given by these two numbers. And that's a lower bound, that's an upper bound. Without me explaining it, this is theoretically stuff you should be able to do. S squared is of the value of the sample variance. On your calculator, you'd find the sample standard deviation and square it. N is the sample size. What are these chi's? Those are critical values for a chi-squared distribution. We did problems like that back in chapter 4, where the subscript is the area to the right. It was on exam 2. First problem on exam 2, I think. You did that kind of problem. So if there's an example, just to make up some numbers here, if we're after a, say a 95% confidence interval, we haven't done a confidence interval in class yet, but I said just use the formula for a problem you had for today. Whenever you have a confidence interval, first ask what is it for? It's always to estimate something. To estimate a parameter value for the population. On your one problem for today was to estimate mu, a population mean. Here in this problem I'm about to make up, we're going to estimate a population variance. CI stands for confidence interval. The 95% is called your level of confidence. The higher your level of confidence, the more confident that you are that the interval captures the true parameter value. Why don't we go for 100%? Why not go for 100%? Go for gold. 100% confidence interval. Because if you go for 100% confidence interval, it's not very useful. Because typically it's going to be the entire real number line. And that doesn't pin value down the value of the parameter very well. So you can't go for 100%, or you don't want to because it's just not useful. So you settle for something less than 100%. Common number is 95%. You could go for 99%, but it's always a trade-off. You go for high confidence, it is going to be a bigger interval, so it's less useful, you might say. So 95% is a common compromise. Notationally speaking, the book writes this as 100 times 1 minus alpha percent. And if 100 times 1 minus alpha equals 95, that means alpha must be 0.05. Weird, but standard. Lots of weird but standard things in this class. Alpha is a way to describe the confidence level via this formula. That 100 times 1 minus alpha is whatever that number is. Alpha is called the level of significance. So we have a level of confidence and we have a level of significance. That only takes its full meaning for us on Thursday when we talk about hypothesis testing. So the confidence interval on your homework for today was written as an estimator, a point estimator, X bar on the homework problem for today to estimate mu, plus or minus something, a margin of error. For estimating a population variance, you don't write the answer in that way. Instead, you write it as an interval from L1 to L2, where according to the formula I showed you in the book, L1 is n minus 1 times s squared divided by chi squared sub alpha over 2, and L2 is n minus 1 times s squared over chi squared sub 1 minus alpha over 2. To use this, you need the numbers. You need to know n. Let's pretend n is 20. You need an observed value of the population. Well, you need an observed value of s capital S squared, called lowercase s squared. Or more likely, from your calculator, you need a value of the sample standard deviation, lowercase s. Maybe on your calculator, you compute it, and I don't know, you get 1.246. You compute s squared from that by squaring it. Right? With a problem, more likely you're going to have to compute that with your calculator's stats functions because you'll have data. So I'm just making up numbers on the spot here. S squared then would be 1.552516. And you figure out these chi-squared values using the level of significance and the degrees of freedom. N equals 20, so the degrees of freedom, lowercase gamma, you could also write it as just df, is n minus 1 is 19. You got 19 degrees of freedom. That affects the values of these chi-squared values here. Gamma, again, is 19. We're after chi-squared sub alpha over 2 is 0.025. And 1 minus alpha over 2 is going to be 0.975. Because alpha itself is 0.05. Look it up in the table or use your technology. Which, without using technology, which one of these two is bigger? The subscripts are areas to the right. Top one's got to be bigger. Smaller area to the right. Oh, let's see. Distribution menu. Oops, I'm forgetting what to do here. There's a chi-squared PDF. Isn't there a chi-squared inverse? I'm forgetting. We really have to just do trial and error with chi-squared CDF. I don't want to do trial and error. Okay, let's use the table in the book. I'm forgetting if there's a chi-squared inv anywhere. It's always so confusing the way they have this inconsistency in how they do things. These are CDF values, areas to the left. We're at 19 degrees of freedom. If the subscript is 0.025, so the area to the right is 0.025, that means the area to the left is 0.975. 32.9 is the bigger one. It's 32.9 there. And the other one is the smaller one. 8.91. Let's check those. So we should get approximately 0.975 here. Yep. And with the other one, we should get approximately 0.025. This is giving CDF values. Yeah. Now use all these numbers, plug in the formula. This is interval notation, left endpoint, right endpoint. It's written as a closed interval. Does you have to write it as a closed interval? No. It's not really a big deal if you write it as an open interval. I mean, we're only doing approximations anyway. For the left endpoint, you got to divide by the bigger number. For the right endpoint, you divide by the smaller number. Our left endpoint is about 0.897. Our right endpoint is about 3.311. So I'm 95% confident that the true population variance is somewhere between these two numbers. And again, it's not a big deal if we used open interval notation. What about the standard deviation? Can I come up with a confidence interval, a 95% confidence interval for the standard deviation? Yeah, take the square root of these two numbers. That's a 95% CI for sigma squared. Take the square root of those numbers. I'll use more decimal places. But then round to the same number here, 0.947 to 1.8. If you round correctly, 20 is a 95% CI for sigma. If we had a different sample of the same size, 20, we would have gotten a different answer. Now, of course, I didn't do an actual sample. I was just pretending to. But in theory, if you did a different sample of the same size from the same population, because of randomness, you're going to get different answers. You're going to get a different S value and a different S squared value, and therefore different interval. Which one's right? They're both right. No matter which random sample of size 20 to compute the interval you calculate in real life here, you're going to get the right answer if you don't make a mistake, because there's not a unique right answer. It's like doing simulation gives you different numbers. Different samples give different intervals. Is that good? Well, it's unavoidable. You can interpret the 95% as saying, if you do the sampling over and over and over again, get a random sample of size 20, compute the interval, get another random sample of size 20, compute the interval, get another random sample of size 20, compute the interval. Maybe do that 1,000 times to get 1,000 intervals. 95% of them or so will contain the true population variance and population standard deviation, depending on which one you're computing. That's the meaning of the 95%, really. But you don't know which of those 5% don't. I mean, real extreme ones, you might say, well, it's not likely to, if you had just an extreme sample. But you never know for sure which ones contain the true population parameter and which ones don't. Today's voting day. Go vote if you haven't yet. The polls will often ask people, who'd you vote for? They're doing random sampling and getting a confidence interval, and they commonly will say, this person got 47% of the vote, plus or minus 2 percentage points. They're telling you a confidence interval there. They're trying to estimate the true proportion of the population that voted for that person. If they say it's 47% plus or minus 2 percentage points, it's between 45 and 49%. They're pretty confident. So the person probably lost if it was only a 2-person race. Probably. But even then, it's not guaranteed. Section 8.2 does the same kind of stuff, except to estimate a different parameter, to estimate the population mean. But wait a minute, didn't we already do that in chapter 7? Yes, in chapter 7, your one problem about this for today was to compute, in the wrong page here, to compute a confidence interval to estimate mu when sigma squared is known using this formula. It's written in, we're emphasizing capital X bar as a random variable. That's the sample mean as a random variable. So this is a theoretical kind of formula as it is. X bar has a distribution. But when you use it based on a random sample, then you can compute an observed value of X bar. You could call it little X bar. You need to know the population variance, sigma squared, and therefore the population standard deviation, sigma. Is that realistic? It's not realistic. Why would you know sigma if you don't know mu? That's crazy. I'm serious. That's crazy. So why do we teach you this? Because it's a stepping stone for a more accurate thing to do or a more realistic thing to do. That's why. People actually still use it. They pretend like they know sigma. Just because of what I'm about to show you in 1 minute is more complicated. Z sub alpha over 2. Yeah, okay. If it's 95% confidence, alpha is 0.05. Alpha over 2 would be 0.025. This number ends up being 1.96. N is the sample size. Use the formula. This quantity here is called the margin of error. Such an interval will be centered on X bar. With the interval we computed with the this formula, it's not centered on S squared. These numbers, the left and right endpoints, are not equidistant from S squared. So that's why we don't use the plus or minus notation here. Because the chi-squared graph is not symmetric, whereas the normal graph is. That's what you used. And that is what is most accurate if you pretended like you knew sigma. But again, why would you know sigma if you don't know mu? They're both population parameters. You probably have to estimate them both. And that's what we do in chapter 8, section 8.2. We replace sigma with S, capital S. Sigma is a number. Capital S is not a number. Right? Capital S. It's a random variable. So what I'm about to show you in chapter 8 makes not only the point estimator a random variable, but the margin of error is a random variable too. And if you make that a random variable, you got to pay a price. You lose a degree of freedom. What's in section 8.2? My book is falling apart here. 8.2. That looks pretty similar, doesn't it? Yeah, sigma got replaced with capital S. Wait, what's that? T? What's T? T is a new distribution. The T distribution. Also called Student's T distribution. Discovered by somebody with the last name of Gossett. Not Nathan Gossett. Not Eric Gossett, if you've heard of Nathan Gossett's dad. A different Gossett. Actually, they spell Gossett differently. They just have one T at the end instead of two T's. Did we talk about the history in here? I forgot. I'm not seeing discussion of the history in here. T distribution has a very interesting history behind it, related to corporate competition and intellectual privacy, intellectual property. Look it up. Pretty interesting. Maybe I'll talk about it on Thursday. What is a T distribution? There's its PDF with some typos, with a typo. It's on page 264. That's a T distribution PDF with little gamma degrees of freedom. And the capital gamma is the gamma function. Do you need to know this PDF? No, you don't typically need to know it or use it, but if you want to use it, you could. With Mathematica, probably. Otherwise, you just use technology or the table. Little gamma is called degrees of freedom. You could have 1 degree of freedom, you could have 2 degrees of freedom, you could have 3, etc. There's this PDF. How is it relevant? According to this theorem, or this definition, and another theorem that I'll show you in a minute, it's relevant. If Z is standard normal, and capital, is that an X? That's actually a chi. It looks like an X. Capital chi sub little gamma is an independent chi-squared random variable with gamma degrees of freedom. Then this crazy looking random variable, Z divided by the square root of chi squared over little gamma, is a T distribution with gamma degrees of freedom. What? Who thought of this? Gossett did. How is this relevant? That's not clear. How would you figure this out in the first place? That's not so clear. That could be another project this weekend. Where did they come up with this? It is actually related to multivariable calculus in doing like double integrals. You can derive joint distributions is how you can derive this. It's really, okay, this is a definition, not a theorem, so we're not really proving it. We're just sort of trying to justify why it's a good idea. You don't really use that definition in our course, at least. It could be relevant in applied stats. You don't really use this PDF. What you do use is you use your technology as well as these theorems. What's going on here? We're standardizing. Look at that. Take X bar, subtract the mean, divide by, is that a standard deviation? Almost. If you got a random sample from a normal distribution with a mean of mu and a variance sigma squared, then this random variable follows a t distribution with n-1 degrees of freedom. That is actually kind of related to that definition. Yeah, we can relate it to the definition down here. We can see the proof of this not too long. So you can use that definition for this proof. It is kind of standardizing here. Okay, what do we know about X bar? There's an X bar in there. This is where we finally get back a little bit to the central limit theorem. Hang with me, just 5 more minutes. Hang with me. Hold on tight. Chapter 7, we had the cornerstone theorem. Fingerprint theorem, cornerstone theorem. So many theorems. Cornerstone theorem was this one. If your random sample is from a normal distribution with mean, mu, and variance sigma squared, then the sample mean, we already knew it had mean, mu, and variance sigma squared over n. The new thing here is that it's also normal. Having mean mu means it's unbiased. Sigma squared over n is the variance of X bar, no matter what your population is. The new thing is that X bar is also normal. Related to this cornerstone theorem is the central limit theorem. Sorry, so many flipping through theorems here, but it's important. X1 through Xn is a random sample from a distribution with finite mean mu and finite variance sigma squared. The word finite is not in there, but it's implied. Then for large n, X bar is approximately normal. The word normal is not in the first sentence. How'd it come in the second sentence? That's the amazingness of this theorem. Approximately normal with mean, mu, and variance sigma squared over n. And if you standardize, so to speak, subtract the mean, divide by the standard deviation, you get an approximately standard normal random variable. How could this be a theorem? Large, approximately. How do you prove such a thing? This is Dr. Wetzel would say this is a result, as it's stated here, not a theorem. Theorems have to be super duper precise so you can precisely prove them. This is not really a theorem, even though you see the word theorem there and there, because it's too vague, but it's good enough for us. We'll call it a result, but I'll still call it the central limit theorem, CLT, because what else am I going to call it? It's too vague because of the words like large and approximately in it. But it's good enough to say, okay, this is approximately normal. In the theorem in chapter 8 that I was just showing you 2 minutes ago, this is the same thing we saw there, except it was an S instead of a sigma. S instead of sigma. It's no longer approximately normal. Well, you could still say it's approximately normal, but more precisely, it's got a t distribution with n minus 1 degrees of freedom. Though if n is large, t distributions and normal distributions are approximately the same when n is large. They both have bell-shaped curve for their PDF. This is the basis for hypothesis testing that we'll talk about Thursday. For your homework due Thursday, you'll need to use this theorem. And to use it, you'll have to find t sub alpha over 2. That could be done on a calculator with inv t, which you've never used before. Like if we want an area of 0.975 to the left, because we're after a 95% confidence interval, alpha over 2 is 0.025. And maybe we've got 19 degrees of freedom. We're going to get a t sub 0.025. It's going to be bigger than 1.96. I think it's probably 2 something. Yeah, 2.093. You'd use that for this number right there. You should also, I don't have time to explain it, practice using the t-table in the back of the book. The book does explain it with examples like this. You should get some practice with the table too. Okay, it's a little tricky, but you can do it. All right, have a good day.